Okay, so let's move along. Ben, take it away.
All right. So I think we're settling down. So this talk is really different than I think what we heard about before. We heard about like language and articulatory technology, and I'm talking about taking seriously articulatory technology and kind of going the other way than most people are talking about. So I got to talk about this. A lot of this comes out of a recent paper. I want to acknowledge that with Adam Lambert, Tom Quattieri, and Parrell at MIT. A lot of stuff that we basically really didn't understand anything, and try to figure it out, and then go over the and what I'm really focusing on today is this level of control, right? So not the level of linguistic structure, not the level of even planning, like how do we combine these gestures and what are the gestures, but let's assume that we can figure that out. Everyone in this room, I don't know if you guys can figure that out. But let's assume we've done that. How do we then go from this plan to actually be able to move the body? That's going. And I want to talk briefly about why we want to conceptualize this in a computational way. So when we have to write down equations, it makes us be really specific. Right? Don't have room for abstraction in mathematics. It's beneficial. We can actually test these hypotheses. Right? We always talk about before having data as like how to actually test the prediction of minutes. And then I think a really powerful thing is that once we have expressed models computationally, we can start to compare models. Right? Compare models from different groups, from different approaches, and see what are we really agreeing about, what are we disagreeing about, what are the points that we need to resolve, be able to move the field forward and understand speech. So I want to talk first about some definitions. So when we talk about tasks, we talk about what we want to do. And I'm using very non-specific language here because I want to talk about models in general. We'll talk about how to space particular technology in particular, but we can think about any motor control issues. So we have tasks, there's some desired outcome of movement, and then a task space in which we can describe that outcome and to describe the state of the system that we're controlling to get there. Right? So for planar hand movements, right, we can move the hand to a position that might be a task goal, and you can describe the task state as the position in some two-dimensional space. But we can also describe what I'm calling the mobility space of the system. This is the state of the system section will change to produce the task. So for a planar arm range movement, that would be the angle of the elbow and the angle of the shoulder relative to the body. Those are the things you can actually control to produce movements in the higher level task. And this is important because we might have some task goal, and maybe we produce a movement and it looks really nice in task space. If we map that same thing in mobility space, right? So we have to distinguish between these two. And particularly not using the term articulatory space, which is the term most people use for mobility space and construction, because I think we understand it here in this room, I think, for the most part, but it leads to a lot of confusions between the fact that the task goals have an articulatory component, and there is a separate articulatory section. Right? So using mobility space to refer to what we normally call articulatory space, right? And we was just described earlier, right? We see parallel tasks, which they can be constrictions for the most part, and this mobility space, which is the parts of the body that are actually producing. So how do we actually move? There's basically three types of movements, or three types of generated movements. If you think about it from a control theory, have a feed-forward control where basically plan a movement in advance, and then as we go through time, just sort of execute that movement. It's called feed-forward because we're not using feedback to control it. Often it's control. We can use feedback control. So generally in a feedback control system, you sort of specify the end goal, you sort of measure where you are in relation to that goal. That generates an error distance from the goal, and sort of use that to somehow generate one. Simple and more complex. And then lastly, we have what we've been calling model predictive control. This is very similar to feedback control, sort of measure where we are, measure where we want to go. But the difference is we don't actually measure anything, we just sort of have an internal estimate of where our body is. So we can sort of generate that error without actually having to measure the body. We know where we are, maybe we don't have to know, but use our senses. And so from a I'm going to do a lot of box diagrams. So if you're not familiar with engineering theory, engineers love boxes, what I've learned over the years. So we're going to talk about control theory using these boxes. It's going to help us understand at a deeper level. So in a feed-forward control system, you have this planner. Right? This is generating motor, generating what we want to do. It's going to output some reference, which is going to be typically for a feed-forward control system with respect to time, saying each time point where I want to be. We're going to have a controller that takes that reference from the planner and converts it into a motor command that the plant can actually operate on, the body can operate on. And notice here that we have this transformation now from task space, the x's, to mobility space. So that's what the controller does. It converts these things from sort of abstract goals to movements that we can actually produce. And then we have the plant, which is the body, which moves. And generates potentially some sensory feedback, although in this system we don't really care what the sensory consequences are. So go ahead and do what we want to do, doesn't matter what that. So feedback control system is very similar. We have this planner that's outputting a reference, but then that reference doesn't necessarily specify what to do, it just specifies for the end goal. So we need to actually compare where we are to that reference. That's going to generate some error. Right, the difference between where we are and where we want to go. We can use that error now to generate a motor command rather than using it. So that's a typical feedback control. Model predictive, very similar. The difference is that instead of using actual feedback, we take that away. We take a copy of that motor command that we just issued, often called an inference copy, generate an estimate of where the body is based on that inference copy, and then use that to do this difference equation to generate this error. Right, so it's the same sort of architecture, it's just we're not actually measuring where the body is, we're sort of guessing where the body is. And as long as you're good at guessing, it's fine. And if you're bad at guessing, things start to so we can combine these in different ways. So these are sort of three basic architectures. I'm not going to go into why these three basic architectures aren't right, but they're not. So we can combine them in different ways to get a more right system. So we can combine like a feed-forward and a feedback controller. This is nice because it sort of allows us to pre-plan things and move fast, but we have sensory feedback long. So sensory feedback takes a long time to predict the system. Right? We're not robots. Robots can use feedback really well. Humans takes like 50 to 150 milliseconds to actually get feedback and act on it. So sound like short feedback, so not really. We can also combine a model predictive controller and feedback controller. So same things, feed-forward and feedback. Now we sort of replace that feed-forward with model predictive. This is sort of the simplest way you can do that. It turns out there's a lot of ways to combine model predictor and feedback control. So this is one. Another one, which is called a Smith predictor. We start with a sort of basic model predictive controller here, and we just take away this direct link from the model to the comparator. And instead we use that model to generate what I'm calling a state prediction, which is basically a state estimation in progress. It's not final. We can use that prediction to compare to sensory feedback, and then use that difference between what we expect to perceive and what we actually perceive, sort of change our state estimate to generate more accurate state predictions to generate more accurate state estimates. Okay. So this is really useful in robotics. It has a very long history. There's another way to do this. I'm not going to talk more about this, but it's sort of intermediate steps. Okay. The next thing, which is going to be important, is this idea of what's often called a common filter or a state feedback control. So we still have this inference copy coming from our motor commands. We're still using it to as the input to a model that's going to generate some prediction. That prediction is the same as before, but now we're also going to generate a sensory prediction. So not only are we going to generate a prediction of where the body is, but of the sensory consequences of being in that state. We can then compare that sensory prediction with the actual incoming sensory feedback and use that to correct our initial estimate to generate a more accurate state. The key here is that this is not a linear process. It's not a simple additive process like it was in the Smith predictor. Here we have this thing K, this equation, this Common gain. I'm going to talk more about that later. But the critical thing is that Common gain sets the weight for the feedback, and that weight is proportional to how much we believe that feedback to be happening. So both really confident that the feedback is good, we can really rely on it. If we think the feedback is pretty crappy, we can just mostly ignore it, right? We won't go with them anywhere. So I'll talk more about that. So just to show you that these ideas have a long history, this idea is not old. So in 1954, Parrell had his model of speech as a servo controller. Servo controls network, right? So this is a very old idea, the idea that we're using sensory feedback to guide speech. I'm not going to go through this in detail. It's all different terminology. Read the paper, it's short and good to read those. So let's think about how we can understand task dynamics within this framework, right? So we have this planner, which is essentially going to generate a gestural score, potentially with some other exotic things on top of it. And what this ends up looking like, I don't know. But let's assume that we have it. We're going to output our gestures, which is essentially our gestures are our reference signal, right? There are goals of what we want to do. Then we need to compare that to where we are. So we have a feedback. So for task dynamics, we measure the state of the plant, right, in Casey. We get that position mobility space, and I think this is, I know this has been a point of confusion. It took me a long time to find this quote. It's going to take the website as much. The assumption, I think, the original assumption in task dynamics, and if I'm wrong, you can ask other people who were there. That this, like, the idea is what they weren't necessarily interested in, like, how do we actually know the state of the body, right? That's a neuroscience question. How do we measure the that? Let's just assume that we can know that, right? And that's the assumption that task dynamics makes, is that we can just know the state of the body sort of in real time with no errors. And that's the sort of simplifying assumption. But let's assume we can know that, so we can measure the state of the articulators. We can use then that forward kinematics model, that Jacobian that we were talking about, to go from the state of the articulators to the state of the tasks, right? And now we can use this in our feedback control system. And so it's complicated, but follows the architecture of feedback control system, right? The difference is that we're going to generate, use that error now in this feedback control law. This is where the damping and the mass coefficients of this dynamical control system happen. And so you can imagine there's also an arrow coming from the planner to the feedback control law that's saying not only what are the spatial goals of the gestures, but what are their other dynamical coefficients. We also need to know the velocity of the system. This is the second order system. So it's not just enough to know position, we need to know the velocity. And then we can use all of that information to generate an acceleration task space, desired change, and then through inverse kinematics, which is hard, but again, given the sort of simple casing model, we can calculate the pseudo-inverse of the Jacobian, and if we know where we are in space, we can use that to generate an acceleration in the casing parameters that's going to move the system on. So there's a lot of math behind here I'm not talking about. This doesn't make sense. The general idea is it's a feedback control, right? It's a complicated feedback control. And this is great. So it's a feedback control system. So what can we do with it? Well, really early, Elliott showed that there's this. This is a result that shows that if you pull down on the jaw, people are producing above. People compensate by moving the lips more than they would otherwise. And so Elliott from 1986 showed this. Right, this is a model simulation. This is the jaw open. This is a B normally. And if you put the jaw down, right, the system is able to compensate. So that's great. We're able to reproduce real speech behavior, which is always the goal. But Lewis kind of alluded to this, that sensory feedback and speech production is a lot more complex than the traditional treatment in this community. So speech is responsive to sensory feedback. So we saw our able to compensate for these somatosensory perturbations like jaw pulls, like pulling on people's lips, all sorts of things like that. But we also compensate for auditory. So if you have people speak and you perturb their auditory feedback, they're going to make a very responsive to that perturbation. That doesn't fit in the task dynamics model. There's no auditory. It's only somatosensory. So it doesn't really work. The weird thing about speech, though, is that you don't need sensory feedback. So it seems that you use it if it's there. But we've all had the experience of talking when you can't hear yourself at a concert or whatever. Doesn't mean you can't talk. So you don't need auditory feedback to talk, but it's there to use it. And to some extent, it seems to be purely tactile feedback. So if you sort of mask tactile feedback with oral anesthetic, people can talk. They're a little worse, but they're pretty good. I had this like great idea about why can't we not mask proprioceptive feedback? So proprioceptive is space, feedback. So I looked into it and I was like, this is great. You know, I teach anatomy, so I should run this. Proprioceptive information is very like a Russell nerve, that's the nerve that integrates the mind. So if you mask proprioceptive information, turns out people can't talk because they can't hear it. So somebody did it. Maybe it's quite this. It's not super. So we don't really know about proprioceptive feedback. It's hard to mask, but in theory, proprioceptive feedback might have larger deficits. Like monkeys that lesion their proprioceptive feedback and can't do very well. There's some evidence that it might be more important than because what we can do. So I want to show some work now. I'm just going to show a little bit of work I've done. How do we put past dynamics into a more realistic placement that accounts for some of these factors? So this is a FACS model, which is a full-on acronym. Sounds good, right? So it's the feedback-aware control of tasks speech model, which is work that I'm doing with John Hood, Trina Rajan, and Vikram Ramanarayan at UCSF. And the idea is how do we account for auditory feedback within testing? That's what we're doing. And the idea is that we're going to sort of eliminate this direct measurement of sensory feedback. And instead, we're going to replace it with that So we're going to take a inference copy of that motor command. We're going to predict the state of the plant. We're also going to predict the sensory feedback. We're going to compare that sensory feedback that comes in. Now, not only somatic sensory feedback, but also auditory feedback. We're going to use that to generate some correction, better prediction, generate a final estimate, to do all the other things we do with that estimate. So what are the files? Why do you think it's good? Well, we can account for the lift perturbation itself. Elliot already showed you the original plus dynamics, so we can use that. I was going to say we're going to try to make the model better. But what we can also do is now we can account. We can also account for auditory perturbation. So here's a little experiment we did with the model. We had the model produce like a sound. We turned on this perturbation of F1, where we just added 100 Hz to the F1 signal the model was receiving. And you can see that it starts to compensate for this auditory perturbation online, mimicking what real people do, which is nice. But there's still no auditory goals, right? So people sort of use this argument to argue that auditory goals exist. I'm not saying that they don't exist. You don't have auditory goals to explain this. But you can still get this suggestion. And we get this because the auditory information can be used to generate that complex. All right. The other thing I want to show is this kind of gives the window into this idea of variability and you don't need auditory information to speak, but it's sort of easy as possible. So if we look at the variability the model produces, so we have noise in the system, which is an important part of this model to be able to use the common filter. So this is just normal production. The other nice thing about the model, I think, is we move away from aspect of test dynamics. We're producing some variability now. Better approximating the people. If we take away auditory feedback, we see a little bit of increase in that variability, but not a lot. Which is good, so awesome. If we take away proprioceptive, we see a larger increase in that variability, which is matched up with the experimental evidence. And if we take away all the feedback, we get good, right? Because we're only relying on our instrumental model now, and our instrumental model is apparently has some. So I think this is a pretty nice target replicate what we expect to see. The other thing the model predicts is with this observer, right? Going back to this idea of the common thing. The common game has this inherent reliance on our internal estimate of how accurate, as well as our estimate of how accurate our prediction. And it makes the prediction that if we change how accurate the sensor systems are, we can change how much we respond to prediction. And I'll come back to the point later to the video for some of those ones. What I want to show first is we see that. So we increase the auditory noise, we get a smaller response. We decrease the auditory noise, we get a larger response. And the same thing happens for somatosensory noise. So if we increase the somatosensory noise, we will have more auditory feedback, a larger response. If we decrease the somatosensory noise, we will have less feedback. There's some evidence that this might be true, so people tend to respond more to auditory perturbations or somatosensory perturbations across the population. This is again medical. So it suggests that maybe this is getting at something true variation across people and like how accurate our sensors are. The other thing it raises the question of, Lewis mentioned that earlier, the tasks might have more complex goals, right? So maybe our acoustic task goals. It could also be that the tasks themselves are modulated by common gains, but for vowels, we might care more about auditory feedback to seem inherently more informative than for consonants. Whereas for consonants, we might get more, so might simply feedback to be more informative. So I think that's a nice idea, and we're exploring about how different tasks might modulate this low-level consonants. All right, so this is where we are with facts model, and I want to point out one thing. I don't want to say that like it's good that we agree with other fields, just that that's good. People other fields might be wrong, but it turns out we do agree with other fields, so it's nice. So this is like the sort of dominant model of air control right now in wind control and auto control, optimal feedback control. You can see that it's very similar to this enhanced fast dynamics with a common thing. So we have a controller, we have an inference output which generates a state estimate. We're measuring the state of the body and using that as the estimate as well. So it's a nice model, and what I like about it is that it generates the estimate. So this is some experimental data from Stephen Scott's paper, 2004 review paper. So C is a sort of feed-forward model, or this is arm-throwing data. So it's simulated arm-throwing. What's shown in C is a path to some complex space of the arm trajectory where you're trying to match a particular trajectory. Okay? And you notice the variability along that trajectory is really small because you're always trying to match the trajectory, but the variability at the end goal is really big. In this optimal feedback control, which is on the right, the trajectory itself can vary a lot. Right? Because you're not controlling the trajectory explicitly, you're controlling some high-level path, and the end variability care about is small. Right? So it fits well with, say, an animal systems control, or we care about some particular high-level task. We don't really care about each moment in time exactly what we do. And it naturally experiments get a lot better than that. So all this being said, I think we're on the right track with the sort of feedback control of the and the last thing I want to mention in terms of other dimensions where we can go with this. So this is new work that I have with Adam Lemmer, thinking about how do we model behaviors that might not be capturable with simplistic approach. Right, so right now, every gesture is a second-order dynamical system with a whole of systems, which has explained a lot, but might not be able to explain. So can we increase the complexity of these dynamics to better approximate DSP behavior? So one way is to use more complex dynamics themselves, like Thornton and Mondes and stuff, that are using higher order systems. We're using a different approach here, which is borrowed from Stefan Paul, that he was seeking about called dynamic movement primitives, and the idea is that you can add a forcing function to this feedback control law that's dependent on the gestures, but is not necessarily part of the same gesture. So basically being able to change the dynamics in more complex way. I'm not going to go into a lot of these, but it's part of it. I'm happy to talk about it later. The idea is that you create a forcing function. The forcing function is there in red, and you can alter the trajectory in it. So on the top panel, we have in blue sort of a critically damped mass spring trajectory. In red, we sort of modify that trajectory. And so it gives us power to modify these trajectories. And what we're able to do is replicate something that I don't think is applicable in the system framework, which is this thoughtful predictive control. So basically, they hook people up to a robot. The robot hold on to this dog as they're using and the force load is lost with them. The faster you move, the more you move. And what they showed is that so the black trajectory on the right is the jaw opening trajectory at baseline. When you initially put people in this force field, this was the jaw pulled forward. That's the blue trajectory. After 500 some trials, you measure the jaw again, and it returns to the straight jaw trajectory. And we know the green is really important here because we know that it increases the stiffness of the system. So you can overcome this perturbation by just like being super rigid, right? And just sort of tensing everything. That's not what people do because when you take away the perturbation, they show an after effect. It's just they really change the control at they're really accounting for the dynamics of the system. So we're able to do this through an optimization framework where you have a very simple sort of jaw system. The point here is on the bottom. So we have this is a baseline trajectory of jaw opening from top. When we put people in the force, we put the model in the force field. We put the model in the force field, we get this trajectory that's deviated to the right, and then after training through various optimization algorithms, we get this return to this straight line. So we're able to account for these extra dynamics in a way that seems relevant. And how relevant this is for like every basis, I'm not sure. We can talk about that. Maybe, but it seems like it's at least something to be accounted for to account for this experiment. So now that we need it, what else can we do with it? And then the last thing I want to end up with is discussion of other models, because I think I didn't know them. I think maybe others did. I think it's important to talk to people on the other side of it. So I want to talk a little bit about DIVA. So DIVA is the directions and velocity particular models and benefit models. And we can understand it in the same framework. So DIVA essentially has a reference trajectory that's issued in mobility space. Mobility space and passive space are the same. And that is combined with another reference trajectory that is issued in semi-century space, and a third reference trajectory which is issued in power space. So 3 tasks going on at once, all trajectories through this. That mobility space reference trajectory is used in a model predictive controller to generate sort of a term called a feed-forward command. We have a long disagreement about whether it's actually forward model. It's essentially a feed-forward controller to generate movement. And then we have 2 feedback controllers, now sensory and audio. So, in a question of where do we agree and where do we disagree, I think there are important questions. The points of agreement are good and the points of disagreement are good. So, if we compare DIVA and test dynamics, there are really 2 good models out there. We can see that both are sort of release feedback control and we allow for sort of fast collaboration of test dynamics. They both also use model predictive control. They both issue their reference trajectory as a function of time. In DIVA, that's an explicit trajectory. In test dynamics, that's a time varying control law. Right? Just score has explicit time in it once you get to that level. They both use the pseudo-inverse Jacobian, and that can use in task space and use in mobility space. That comes with some of their needs. They both sort of implicitly use the assumption that you can dominate control muscles, that you can do all speech control at an high level, not at an level, which, I think there's some evidence that probably knows. And they both sort of use sensitivity. They disagree on a lot of points. What are the task spaces? I think that's an important point of disagreement with you in the context. Trajectory versus point tracking control, or that is how they differ. the targets regions in space or are they points in space? Whether those are time varying or whether they're static are different. The serial versus parallel architecture, and DIVA has a nice model of adaptive control. How can you change control over time to monitor changes in the local graph, changes in the arbitrary feedback? They're really different how such are generated. This goes back to this talking about before. There's this suppression of expected auditory feedback at the middle level. The question is, do you generate that because you have a plan and acoustic target, or do you generate that because you're generating a sensory prediction of what you expect? So they're fundamentally sort of different ways of getting it. And then the last thing that I think I want to talk about is this idea of kinematic versus dynamic control. There are models of dynamic control. This is called Parrell's model, the Parrell model. I'm not going to go into detail, but it's a biomechanical model that has a mobility space of muscle. And it's compatible in various ways with these other models, but maybe an important point for some issues of control are really about the mechanics of the plant. There are ways to do that, whether you want to explore those ways.